Hello and welcome to our MIT808 capstone presentation. For our project, we partnered with the Forestry, Agriculture and Biodiversity Institute of South Africa, also known as FABI. We were provided with the weather records of over 6,000 weather stations across South Africa for the last 70 years. We were also given the inspection records for two types of invasive pests known as Leptocybe invasa and Sirex noctilio. This project aimed to determine if any relationship between regional climatic patterns and pest prevalence could be uncovered using machine learning techniques. Before we start, we will provide a brief background on the two species of pests discussed in this project. Leptocybe invasa, also known as the blue gum culcid, is a small black wasp native to Australia. These wasps lay their eggs on young blue gum trees, which creates abnormal growths on the plant's leaves, petioles, and stems. Severely infected trees may experience stunted growth or even death. Sirex noctilio is the larger of the two pests and originated from Eurasia and northern Africa. These wasps primarily infect pine trees by boring into the trunk to lay eggs. The eggs are deposited with a mucoid substance that is toxic to trees. The pine needles of infected trees generally turn yellow or brown within a month after the eggs have been laid. Furthermore, larval tunnels can be observed in the tree sapwood, leading to a further decline in health. On the maps provided below, we can see that the inspections for both pests are primarily conducted in or around the coastal regions of South Africa. The user can also select a particular year should they wish to investigate pest prevalence on a more granular level. Lastly, the contributing reports are made available through these download buttons. To find out the exact technical details behind this project, you can visit the FABI website or the GitHub repository by clicking on these links. To address the machine learning component of this project, we have developed a predictions tab in our app. The user can choose between a pre-trained support vector classifier or a pre-trained XGboost classifier. Once a model is chosen, the user can select their inputs, which will be processed through a complex feature engineering script to generate 8 more features required by the two models. The map on the right shows the approximate location of the prediction, and when the Run button is clicked, both pests are simultaneously predicted. The user is then presented with the prediction, the class probabilities, and the rock-orc curve of the model. Lastly, we also explain the model for any non-technical users of the app.
The results of the model are then fed to the visualization page. Firstly, we show the total rainfall and average maximum and minimum temperatures per year for the selected month and location, dating from 1950 through to 2019. These graphs also show the measurements previously provided. This is to allow the user to view the change in weather trends compared to these values. For example, for the maximum temperature, we see that the provided value is much lower than the average experienced. However, the minimum temperature is typical for the area. The second set of visualizations consider the weather stations. When the prediction model runs, a feature engineering script is invoked to firstly find the closest active stations to the provided point per year for the month, and thereafter retrieve the weather readings from those stations. We see that 7 unique stations provide weather measurements over time. Station 996 and 993 are located less than 10 kilometers away and provide data from 1950 through to 2000. Thereafter, the weather stations change, indicating that the prior stations were either decommissioned or the data is incomplete. The stations are also displayed spatially. If we zoom in, we can see that station 996 and 993, as well as all the other stations used for the data. Thereafter, we have the pest prediction at our location with the input and the result from the prediction page reiterated. The average measurements from above and the difference between the average and the inputs are also shown. Lastly, we have the pest prediction across South Africa. These maps enable the user to compare the prediction probability at the current point and the probability across the country if the same input weather conditions are experienced. Note that the stations used per grid block are specific to that block, providing a unique weather pattern. These maps are particularly useful to compare the results for the provided location against those in the vicinity to identify areas that are more prone to infestation. For example, we see that the positive Leptocybe probability is only 30% at our location, but just 50 kilometers north, the probability is 53%, and near MIT808, the probability exceeds 75%. Finally, the upload page allows the users to upload their records. FABI requested this as surveyors need a tool to upload data collected during inspections. That concludes our capstone presentation. Thank you to our partners for this exciting project to use big data science for problem-solving initiatives.